Hello everyone. Wow, this is great to be here. This is like the first time for me to talk in such a big audience and streaming live. So this is awesome for me, I have to say. So I'm talking about everything you don't want to know about async and await. So for a little motivation, I want to start up a quick WPF application that I built for this presentation. And via this button, I would be getting the download of this package and of the Microsoft.bcl.async interfaces package. But when I click this button, I see that the clock isn't ticking anymore. And now I don't know, is the UI thread, is it hanging as my application froze, or am I actually deadlocking? And asynchronous programming is one of the things which could solve such issues. We want to keep our threads responsive, especially our main thread if this is a UI application. So, my name is Stefan Pölz. I refer to myself as a clean C# coder and a test-driven .NET developer. I'm coding since 2008. I started out with C++. Then in 2012, I shifted to C#. I started out with Mono, and in 2013, I went to .NET. Async await I'm doing since 2015, and pretty much doing it like, yeah, every day. Currently, I am in Vienna working at Alternative Services. We are building for the energy market. We want to automate things and make our services very accessible. And there's a lot of web and via cloud services, so asynchronous programming is something that I have to do with every day. Here are some of my alter egos on the web, but I come to that later on. To the table of content. So why async await? What problem is it solving? We want to use our threads efficiently. We want them to lock them up. So what you just now saw on the UI application, we don't want to block our UI thread. This is that we want to keep our apps responsive. And the same goes for server applications. We don't want to block an entire thread, just waiting for an I/O access, like requesting a different service or reading from a file. Because while this I/O process, this operation is happening, the thread could do something else. So we don't want to block it. We want to be responsive. We want to answer the requests from our users. And the keywords for that are async and await in C#. We will have a look at related types in the framework from the from the system namespace. And we will have a look at asynchronous operations and about continuations to those operations. We'll have a look at the control flow and the async state machine. So async and await is actually C# magic, which then generates some code for us for the compiler. We will have a look at cancellation in .NET, that's cooperative cancellation. We will have a look at progress reporting and some new features like the ValueTask. Well, not so new, but the newest feature is asynchronous streams, where we had interface IAsyncEnumerable. So let us first clean out some terminology. So concurrency is the term in general to refer about doing more stuff than just once at a time. One form of concurrency would be multithreading, utilizing multiple threads from our CPUs. One form would be parallelism, working on data in parallel. One form of concurrency is asynchronous programming, which I will focus on today. And another form is reactive programming. This is not directly in the .NET framework, but there are several extensions, namely the reactive RX extensions, where we could do reactive programming. So you may have heard of the TAP, that's the Task Asynchronous Program Model. So there are two statements. The big advantage of using async and await is we can write asynchronous instructions and the code still reads rather synchronously. We don't have our continuations jumping around from one block and to a lambda there and to a different method over there. It reads rather synchronously from top to bottom. Of course, there is some control flow change, but via this programming model now, handling exceptions comes very naturally. And one term that I want to definitely clear out is the difference between IO-bound operations and CPU-bound operations. So async await is definitely for IO-bound operations. While we are waiting for an IO task to complete, for example, reading a file, reading a stream, having some web request going on, that's what async await is naturally for. CPU-bound operations, there are better techniques to solve that, because we could start up a thread, put it into a task, await that task, but if it is CPU-bound, this thread, if it's heavily CPU-bound, this thread would still block it, wouldn't do anything else. So it's not really async. But for that, I like to refer to the talk Martin gave like 1.5 months ago. Hardware intrinsics is one form of increasing the throughput of CPU-intensive operations. So let's have a look at the control flow in an asynchronous program. So we have our modifier here, async, and this enables the await keywords in asynchronous methods. And the control flow goes basically from top to bottom. So we start, when we call this method, we start synchronously from top to bottom. We call into this method, which puts out some information. Then we call into this method, still synchronously. So this is some angle sharp code, if you know this library, to access, to parse websites. We are then opening a request, starting the web request, and pretty much every method, this is the convention, postfix suffix with async returns a task or a value task or something which I can await later on, which holds the operation which eventually complete. And when I then await this operation, and this operation has not completed yet, then the control jumps to the caller, which is, we call this method. So we will get here now this task, which is not completed yet. It's running, it's not in a completed state yet, it's incomplete. And control goes on until we hit the next await. And again, we check, is the operation complete? When not, we give control back to the caller. And this goes up to the main, until to the main method or to some event handler. And at some point of time, this operation down there completes. And then this continuation is scheduled back, and we will then continue running there. We have this document, and I can return the title, which then now finishes this method, which means that this task is completed. And then this method continues here. We set the title and put it onto the console. So let's run this app, and we see that we first start out synchronously. We're starting the web request down here. We are waiting the web request. Now the web request is not completed yet. We give control back to the caller, which is now up here. We await this operation, which now again is controlled back until this operation awaited first is completed. And returns the path, so we completed the web request, and the application comes to an end, and we pull out the title of this web request. So let's come to the keywords, async and await. They're available in C#5. With C#8, there was IAsyncEnumerable and IAsyncDisposable added. So async is a contextual keyword. It modifies methods, lambda methods, and anonymous method. And so we can actually write something like this. So this down here is not the async keyword, it's just an identifier, could be anything. But this here, because this is the lambda method, this is the identifier, this makes the keyword, this makes the method asynchronous and enables the await keyword for us to await something awaitable. We will come to that just in a bit, what we can await. What are those async return types, which are returned from asynchronous methods, mostly suffixed with async. So we have task, we have task of t, where task basically would be, if it would be a synchronous method, would be void. The task of t would be some method returning a type. We can write async void, but I strongly suggest not to do. The only exception would be event handlers, because they have to be void. They can't return anything. This is the only exception. Otherwise, we will have issues. We will come to that later. And in C#7, we can pretty much await anything which implements iNotify completion or iCritical notify completion. And we need an accessible getAwaiter method. For example, there are now those new types, ValueTask, ValueTask T, which provide low allocation or no allocation methods to increase the throughput, especially of web applications. And yeah, we also talked about asynchronous streams via the IAsyncEnumerable. So in asynchronous methods, we're not allowed to have in, ref, or out parameters. And we can't put ref structs or ref return values in them. Because of state machine, we will have a look at that in a bit. So the second part of the async await, the await keyword, which is enabled by the async keyword, can be applied to an operand, can be applied to something which is awaitable. And then if checks if this awaitable thing is completed yet, it just continues the flow just synchronously. But if this operation is not completed yet, the control will be suspended and given back to the caller, and he then has time. So eventually it goes back to the main thread, and eventually the thread may be free and do something else, whatever that the thread pool schedules. We cannot await in a log statement or an unsafe context. So if we still want to have a lock, we can use the semaphore slim for that. For example, here I have a quick example which creates us a enumerable, and we select all of them, but this resource is modified by all of them. Then we are task yield, we await, so all of them return back the control. And once this is continued for the first, which actually it's there, the last one actually has modified this string, and so it's all the same. So I can put here via the semaphore slim. I can write wait async that I will await, then put the core of the method into a try catch block, into a try finally block. And in the finally, oops, we now release the mutex, and now we just, now this resource is locked, and we have just the same order as this enumerable is generated. So the awaitable expression, this I mentioned already. So if we await either task or value task, it evaluates to void. If we await a task of t or a value task of t, it awaits to this type of t. And we can pretty much await anything which complies with those rules that we implement iNotify completion, which has an accessible is completed property, which returns a boolean. It has get result, either void or this type of t, and a public accessible getAwaiter method. I will show an example about that in later. So let's have a look at asynchronous method and asynchronous operations. So in .NET, those are tasks. In Java, they are called futures. In JavaScript, they're called promises. So it's something, it's a promise, it's a future, it's an operation that will complete eventually. It may complete successfully, it may complete faulted, so an exception happens, or it may be canceled, but eventually it should complete. But I don't know when. It could be completed already by the time I await it, but it may not. So the core types are task, which is available since framework 4 already. A lot of time, this is a usual method to offload some code into a worker thread, and returns it, wraps it into a task, and we can await it. We can check those properties. So we have those 3 states. A task is either completed, a task is either incomplete or completed. And when it is completed, it is either successfully completed, it has been cancelled, or it is faulted. So some other exception than the cancel exception occurred. Task of T result is inheriting from task and enables us with a return type, which we can use once the task is completed. Once this promise is fulfilled, it is promising that the type of T is returned if it completes successfully. If it is cancelled, or if it's faulted, then we do not have this result, but exception. Now there is the new ValueTask and ValueTask of T. I want to quickly talk about them because they have some caveats. They are struct, but they do not have the flexibility and the power of task. Task is a task only completes once. Once a task is completed, it never goes incomplete. A value task may become incomplete again because, depending on implementation, it may use a task pool which will be reused. So only await value task and value task of T, await it or consume it only once. For example, I am here giving the value task in a local variable, so I could actually await this now multiple times. So this is not bad yet, but it may be. For example, if I only do this, await value task, that's fine. If I only a value task with configure await, that's fine. I can do as task to get a task, and then this task I can await multiple times. However, if I would write with a value task something like this, I await it twice. That's bad. We shouldn't do that. Or awaiting it concurrently. We shouldn't do this either. Or synchronously blocking via getAwaited.getResult or via .result. Everything which isn't await synchronously blocks, and ValueTask nor ValueTask T don't have to support synchronous blocking. They may, but per definition they don't have to, and some implementation might not, and then we will run into problems. And then it basically is a race condition: is it done yet or not? However, what is okay? We can check. We can access the is completed successfully. We can access it. And if it is completed successfully, then we can actually use, for example, the .result, but again, only once. And the latest type, IAsyncEnumerable, which is an IEnumerable enabling asynchrony. So I have a quick example. I generate a sequence. I just for each over 9 entries, wait for 100 milliseconds and then return the value. So this is an async method, and it returns the IAsyncEnumerable. This thing, the compiler, in Visual Studio, the compiler warns me if I don't add this this attribute. So this enables cancellation of any IAsyncEnumerable method, but I will come to that in a bit as well. So I'm promising quite some stuff, but I will follow up. So let's have a look. Now, unfortunately, try.net is not .NET Try isn't executing this asynchronously, but I have another example. So I can await anything. So the first promise, promise that I'm not fulfilling, I can await anything when I fulfill those rules that I talked about. So we can write something like, let's jump to my console application. So I have here some await extension. So this is the getAwait, this public getAwait method, which I made available And so this enables me, I then basically just grab a task.delay and get the awaiter. This enables me to await a time span. So I can write, so this is my main method, it's async. I can write await, time span dot from seconds to, and this would be, actually this would be the same like writing await task dot delay with 2 seconds. Will basically be the same, so we can await pretty much anything. Some more types. Cancellation token source. Cancellation token source is one part of cancellation, of this cooperative cancellation. Both parts, the caller and the callee, need to support it. So we can create the cancellation token source. Then there are several ways of canceling. Either we cancel it directly, we can cancel it after, so for a timeout scenario, or for example via an event. Maybe if I press in the console, hit the cancel key, so Control C, then I can cancel this token, this cancellation token source, and I pass this token to the callee, the actual async method, which then has to in return react to it. But I will follow up on that. And the task completion source. The task completion source enables me to build async methods out of, or async types, single async types, via events. So I have a quick example to make a process, to make an async process. So quickly put in the right code. I have, where is it? There is it. So this basically webs, there is some code in here. The most important part is that I have a process where I pass in the start info, and I have here my task completion source, which now helps me to transition so my own task into 3 different states. Either when I complete successfully, I can set the result. When I fail, I can set the exception, so it will transition to the failed state. Or if I cancel it, I can set to try canceled. So let's run it. For example, I'm now executing .NET version, and this little code is then, so I get this process result, which basically holds the exit code and standard input, standard output, standard error, and prints it to the console in various colors. And I now build via all these events. I react, and the task, which I created via the task completion source, I have, if I would start basically now made an async process. So continuations. Once we hit an await, the remainder of once we hit an await and the task is not completed yet, the remainder of the method will become a continuation, which will run once the task has completed. For example, here I can have this type example. I will run the code, then we see what's happening. I will retrieve the task. Then a task, is the task completed? False. No, it is not completed yet. I await it, and now this again with the control flow goes control back. And once the task complete, it is completed, and we have the result available. If I would call result before awaiting it, it would synchronously block, and we don't want to do that. So with this example, I waited the task. I can also just, if it's of task T, I can await it, and then what I said earlier, the result is this type of T, so insert the string. And then there are combinators. Combinators are a way to combine multiple tasks and to wait multiple tasks. For example, here, whenall. So I give in several tasks into whenall, and this returns me one task, which represents the completion of all of those tasks in this group. And there is a whenany, and whenany gives me a task which completes when any, so at least one of those tasks in the group are completed. either successfully faulted or cancelled. So where is this continuation happening? There is a thing called synchronization context. Synchronization context is ASP.NET, WPF, and WinForms are the most prominent examples for which have a synchronization context, especially for UI applications. They need a synchronization context because you can only manipulate UI controls on the UI elements on the thread which created it, the main thread, the UI thread. So we need to be able to schedule continuations back that we can manipulate those controls. For example, console applications and ASP.NET Core, they do not have a synchronization context. So let's fix this deadlock example that I produced earlier. Where is the villain? It is here. Because I do block here, and in the so this is my event handler. The event handler is not async, and I block here the event handler, and this synchronously blocks my main thread because the event handler is called from the main thread. And within my NuGet client, I eventually here have an await, and now they wait on each other because this task is not completed yet, so the continuation is scheduled on the main thread because of the synchronization context. But to find it again, the caller blocks synchronously on this very main thread. So this block and call doesn't release the main thread, but the callee cannot execute now the continuation, which is scheduled. So this is why we end up with the deadlock. Now there are several solutions to it, but the cleanest one would be to make it a sync. So this is now the one exception. I should write task here, but this is an event handler, so it can't be. And now this enables me to await this task. And now, so I can't return the result, so I just await the operation. And now, when I start this application again and click that button in order to get the number of downloads, so it is 672,958 of the Microsoft PCL async interfaces, and so I fixed the deadlock with properly using async await. Now let's have a look at where continuations are scheduled. So we'll toggle this breakpoint here and quickly debug through. So once we come here, we see here we are on the main thread number 1, the main thread. Then I go on, I wait here a completed task. Complete task is already completed, so there it just synchronously completes. So the remainder is still on the main thread. And now we come here to the await. This operation, once the await state is not completed yet, and if I step over it, we will see that we are still on the main thread because this continuation is scheduled always back to the synchronization context, which is in a WPF application, the UI thread. If I do the same thing from a console application, which does not have a synchronization context, I will see that it's still the same thing. So we are on the main thread, and now we hit this continuation. Now we hit the await, but this continuation is now scheduled on the thread pool because console application does not have an implementation of the synchronization context. So synchronization context.current is null, and now this continuation is scheduled onto any thread on the thread pool. Now we see we are on a different thread. We are on thread 7. Now this continuation is on thread 7. So it's much harder, or is it actually possible to produce a deadlock on an environment where there is no synchronization context? And now come to my, configure await false. Yeah, with configure await false, we can force a continuation to not be on the synchronization context. So if I execute, this would be, if I would execute this now again on the, where is it? There is it. WPF application, if I now hit here, configure await false, now this continuation will be scheduled on the thread pool, because with configure await false, I force the continuation not to be scheduled back on the captured context. And this capturing of context is only happening if we are awaiting a task which has not completed yet. So if I do write configure await false here, and I run this application for the last time, at least this code part, and hit get downloads. Now although I'm on a WPF application, so we have the synchronization context, and although I'm doing configure await false, we're currently on the main thread, and if I step over, we still are on the main thread, because this task has already completed. There was no continuation to be scheduled. But now if I go down to this await, now although we are on WPF via synchronization context, we are now so the continuation is now on a thread from the thread pool. So the suggestion is to use configure await false always for library code, because it might end up in a synchronization context aware environment, or it may not. So always use it for library code. Definitely use it on UI applications or on systems which have synchronization context whenever you can. If the continuation would modify a control, for example, some control.text and would write to it, we will get an exception if we are not on the UI UI thread. So use it wisely or with care. And for any system, for example, ASP.NET Core, you don't need to use configure await false, because it has no synchronization context. You don't need to write this code, because it makes code a little bit more, just more code and less code makes it easier to read. So be aware of the framework you run. Now we come to the state machine. So what is happening? What is happening with this? So there is SharpLab, where I can put in code, and then it shows me what the compiler is doing with it. Can you read that? Yeah, all good? So those 3 lines of code with an async method and an await statement now transition to this. So sometimes you may have seen that in a call stack, in an asynchronous method, you sometimes see move next. But where's this move next coming from? In my code, I have no move next. But when I have a look at this generated code, so here's my original code. It has neither the async nor the await keyword. So this is my original method, which is called. And now it creates this state machine. I will just quickly go through the most important parts. So we create here a state machine. We will set the state to -1. We start the state machine, and then we return from the builder, we return the task. And this task, then the caller can await and listen to observe either successful or cancelled or faulted completion of that task. And let's scroll up a bit. Here's now this move next. So this move next is generated. What you see in the generated code, there's always those angle brackets to not mess up. We can write this code, so to not mess up with any potential user code. And this move next is now called for the first time, for the first synchronous call, and then for all the continuations. We go back, like similar to an enumerator, just reiterating the block over and over until the state machine is completed. So we set the state to -1. So we go in here, are we not null? Yes, we are. And here is now actually our first line of code, hello.net community Austria. So we are here. And we see here's now our synchronous code. We haven't done anything with scheduling the continuation or transferring control. Here is now my time-second delay. And now is this check, is this operation, is it completed already? So if it's not completed already, we will set the state to 0, and actually return the method. So this is the part where the control flows to the caller. If this would have been completed, we just synchronously go on. So this is why we don't switch task. It's just synchronous code. If we only await on tasks which have already completed it, the method executes synchronously. And so the state is now, if we now go the second time in, and then the next, the state is O. We jump to the else block, and we set the state to -1, and we see here now our second line of code. That's the third line of code. Goodbye, community Ausüber. Here's always a get result happening. This would rethrow any exceptions. This is how the state machine is observing exceptions. So there is a big try catch over all the state machine, and all the exceptions are similar to the task completion source, where the builder set onto the task. So this is why it is important to always return a task and to avoid async void, because we cannot await void. We don't have this promise. We don't have this task. We cannot await on it. So we will never know when it has finished. We will never know if it has finished, and we will never know has it finished successfully. And this is basically the state machine which is generated. And this may or may not. Maybe have a look at this 2 or 3 times, and this should clear up how this thing is working. And then all the limitations do make sense why this have to be. So some little thing. The state machine is a struct in release mode and a class in debug mode. So when you hit some differences in call stacks and stuff, this is because of that. And this is the state machine which gets generated. So I was talking about exceptions. So exceptions are placed on the task, and we need to await the task or observe this task somehow for exceptions. How can we create a faulted task? For example, with task.fromException. This would create a already completed task which has transitioned to the faulted state with this exception. So if I would await this exception would be thrown. I can in an async method, I can just throw an exception, and what we saw earlier with the state machine, it will be placed onto the task. So this method actually would throw immediately. There is nothing placed on the task because this is just a synchronous method. It returns task, okay, but it's not an asynchronous method. So this would just synchronously throw the exception. And so this is some setup code, and here's now a method where I want to show what is happening. So if I have here now, I call throw async, so this exception is throwing asynchronously. If I do not await it, or if this method would be void and I cannot await it because no task is returned, I just don't know if this exception is actually throwing, but I don't see it. I don't know. So it's not completed. It's not successfully completed. I can't observe the continuation. So always return a task, and if I now enter try catch block, so this is where the async await we can, although with the state machine we can just pretty much synchronously, or the code looks very synchronously, observe exceptions. So I wait on this task, and if we hit this, also I of course have to make the method async to enable the await keyword, and execute it. Now I see that, also yeah, that was my bad. I can return this because now the task is reducing, the state machine is returning the task, and now we actually can observe this exception via just a try catch block. If I would be synchronously blocking on that, so if I would write task dot wait, we do get an aggregate exception. So if we do await it, we just get the first exception thrown, because it is a task, it is a multithread, so a task could have multiple exceptions. And when I await an exception, just the first one which is occurring is rethrown. But if I synchronously wait it, if I block it, if I synchronously blockingly await it, then an aggregate exception is thrown, which has a collection of inner exceptions where I can get to all of the exceptions. And so this is asynchronous exception handling. So cancellation. Cancellation is in .NET cooperatively, so both parts have to support it. The caller needs to enable cancellation, and the callee needs to respect cancellation. Otherwise, it doesn't work. For example, I just have here a callee method. It doesn't get this cancellation token. So the cancellation token is the token that a callee can react on to throw or to cancel the task. It doesn't have a cancellation token, so this is uncancelable. But this callee with the cancellation token, this is cancelable. And it could do it either forcefully, via throw if cancellation requested. This would throw a task cancellation exception. And if a task cancellation, either a task cancellation or the operation cancellation exceptions are thrown, this means that the task is transitioning to the cancelled state. If any other exception is thrown, it is transitioning to the faulted state. So when the token is cancelled, then throw if cancellation token throws this task cancellation exception, and the task is cancelled. We can also do it gracefully by listening to the cancellation and then just stopping the method. For example, we could have a loop, and in each iteration, listen, is the cancellation requested, and if not, continue, otherwise stop it, without actually throwing an exception. So we would cancel it, but gracefully, not throwing the exception. And now the caller, so if I now pass, so we have this, so the caller does have the cancellation token source. It's the source for the cancellation token, and via this cancellation token, we write cancel in order to cancel the token, and we need to pass the token, which is a property of the cancellation token source. The token, we pass that to the method, and now we can actually cancel this method. So I throw, and so I'm throwing, actually, I'm doing the graceful part. So if I swap that out and do the forceful part, now this operation cancelled exception, the operation cancel exception will be thrown, and we will get the message operation was cancelled. And we see here again the properties. So the task is completed. So the task is either completed or not. And if it is completed, it is maybe successfully completed. In this case, it's not successfully completed. It's not faulted either, but it has been cancelled. How do we cancel IAsyncEnumerable? Very similarly. So I set up here a cancellation token source. I cancel after 3 seconds, so like a timeout. In my producer, I have in each loop, I have a task delay. And this task delay also accepts a token, which would then cancel the task with the task cancellation exception. And after 3 seconds, I stop this loop, which is every second returning me asynchronously a new item. So after 3 seconds, I get, because I do not have any code to just for each iterated, I don't have catch the exception, the task cancellation exception, so it is thrown. And another way is to, it's actually the same, I will skip that. So let's come to progress. How can we report progress in an asynchronous method? Via the iProgress interface, and there is a default implementation, the progress. So to the caller, we can pass in the progress, and it can then via, so again, I have a loop, and I then wait for 0.5 seconds, and every 0.5 seconds I report the progress of this method. And then the caller can react to that by passing to the progress a lambda, for example, write the progress to the console. And so we have progress. Now this is a little bit more fancy if we do this in a visual application. So in the WPF application, we can do this with the progress bar. So here I basically hooked up the WPF progress bar. It's basically the same code, but I hooked it up with the WPF progress bar, and we could do something like this. And I also implement the cancellation, so I can cancel this operation and restart it again. So let's come to some common pitfalls that I often stumble upon. So async void, don't do async void, but there may be a hidden async void. For example, when we have an action. So this thing is actually async void because action has no return type, so I cannot await here. So I cannot observe the completion of this task. The correct way would be to have a func of task, because func of tasks now returns us a task which I can await. Another thing that I sometimes see is unnecessary awaits. For example, in this method, I await here, but this await is not needed because there is no continuation actually here. Okay, there is a continuation, but it's empty. So this entire state machine would be built, but the continuation would just execute like nothing. So I don't need this overhead. This overhead can be saved. So I just make this method synchronously and just return the task which is returned by get async, and then the caller has to await anyway. So if there is no continuation, that don't await. Similarly with here, the async lambda, this doesn't need to be async because if I would write this in the block, then it just looks the same like above. There is no continuation or an empty continuation, so this doesn't need to be async. This is something that I saw. How do we create a task? Sometimes I see like something like an empty test.run in order to create a task, but this is total overhead because we spin up a thread on the thread pool, which does nothing just to have a task. So, for example, in testing code or in or when I want to mock something and I want to create a task which has already completed, we can use task.getCompletedTask. Or if I want to create a task of t, I can say from result, of course. Pass in an integer to have a task of integer. Or if you want to create the already completed cancel task, I can say from cancelled or from exception if I want to create a faulted task. So this is fake async. Here we spin up a thread. This might I saw something similar in a WPF application to get work off the UI thread in order to keep the UI responsive. So this 10-second thread sleep represents a CPUbound operation. But if I only have this interface, I only see this method, I would think, okay, it's async, so I can await it and I don't block this thread, or I don't block anything because it's async. So sometimes we can't avoid it. So if you actually do have code which is both IObound and CPUbound, then you have to do something similar to this. But if it is just CPUbound, avoid to do a task sleep, especially in library code. So let the caller of your library code decide if he wants to put it onto a thread pool thread or not, because this would be fake async. Everything which ends in async, I would expect it to be actually async and not blocking. And one more thing, testing. How do we test? How do we test asynchronous code? So I made it looks very similar to all the frameworks. So what we have here, an MS test, and rather than void, the signature just becomes async task. Then we can use await in test code. Or if you want to check for an exception, if an exception is thrown asynchronously, then use throw exception async. Await it, of course. Otherwise, we don't observe the execution, and test may be green, but actually something may be wrong. For end unit, it's a little bit different. on the exception part, because So for any unit does have a throw async method, which accepts an async test delegate, but it does not return a task. It just synchronously returns a value task. So there is no awaiting. So checking for throws actually, this is synchronously. So yeah, this is a style question. And in end unit is very similar to X unit. X unit is very similar to MS test. We have the throw async, and yeah, just use async task if you want to make your tests async. And there is, if you want to know more, there is so much more stuff about it. For example, data flows. Data flows are not in the framework. They are available via this package, system providing task.dataflow. And what it does is we can build a pipeline of data. So several blocks, we can chain those blocks and then send asynchronously data from one block to another. And every block does a small piece of work, manipulating this object or returning new block, returning new results. So step by step, if you have something like a data pipeline, have a look at the data flow. And then there is the reactive programming, which I mentioned earlier. So this is if we IAsyncEnumerable is pull-based. So the caller, the user of an IAsyncEnumerable is pulling with the wait for each, is pulling one element at a time. Reactive programming is the other way around. It's pushing. Via IObserver and IObservable, we would be pushing our data onto the observer. So if you have something scenario like this, no pull-based but push-based, have a look at reactive programming. And there is this namespace, system.link.async. They just recently implemented asynchEnumerable. So all the link names, stuff like range, some create ranges and stuff. Let's have a quick look at it. Are available for IAsync. To find it. Okay, I couldn't find it, but it is if you want to have async link, if you want to have link, and if you want to enable link with IAsyncEnumerable, then check out this package. Because this package is actually using this package that I showed earlier, downloaded earlier. So if you are not using .NET Standard 2.1 or Core 3.0, where IAsyncEnumerable is not available, you can use this package to still have the type IAsyncEnumerable available. And in return, this package, Microsoft BCL Async Interfaces, references system.threading.task.extensions where ValueTask and ValueTask of T are available if you are on another framework which doesn't have those types. So we can get to them. And that now sums up my talk. So do you have any questions? Yes?
How to use async wait properly in a legacy application where I don't have, for example, async main method?
So the main method. So yes, good question. So how do we use async await in legacy applications? The example was in a main application, in the main method, which I cannot make async.
For example, or any other.
So I can answer the main part because actually what this async task is doing, it's calling on an async method. It calls .getIterator, get result. So main method can be async because, for example, console, where does the control flow to? So this is basically what the compiler is doing for us. Now for other stuff, it depends. Maybe let's talk about it later. So it depends. So if you have something with events, if you have events that you can attach to, then you can use the task completion source to generate your task and then set the completion once this event is completed. Maybe we can discuss a few scenarios or do you have a specific scenario?
Or in my case, it was an ASP.NET MVC5 application, web API, I think. And we ran into deadlocking issues where we had to null the synchronization context, and I was hoping there is a definite answer how to approach this issue, because actually the current application is completely without async, written completely without async, and the previous programmer just had task run at every async task. So
and
I was hoping it returns before the request ends.
So in a legacy ASP.NET Core application, in a legacy ASP.NET application where there is a synchronization context, you're doing a lot of task.1 to get the power of tasks. Are those tasks, are they synchronously awaited via task.wait or task.result? So no async await at all.
Nothing waits, everything is wrapped in task.run currently. That's not good.
Yeah, so there is no async await, everything is blocking synchronously. So this is a difficult task for a brownfield. For a big brownfield application, it's actually difficult because async is very viral. So if you go to a library method, and then it doesn't return an integer anymore, but returns a task of int. Now the caller has to await that, and so this method becomes async, and the caller of that becomes async. So this is a big thing. What you can do is do it step by step, making the most important. So we do have a lot of dialogues with a lot of issues, trying to make this async, and then go make it as async up the call free as much as possible. So somewhere to make it step by step, you still have to block to make it a step by step transition. But eventually, you may have one user request which actually becomes async, and there are with task completion source. And with task.1, depending on the task, on the operation you are having, is it IObound or CPUbound. So if you are using if you're reading files, then definitely use the new API and don't do read, but use read async, which returns a task which I can await. And for streams, the same. Use the async API. So over the last frameworks over more or releases over more since task and IAsyncWait came out, more and more APIs got added. So for example, if you still have the web request switch to the HTTP, the web client switch to the HTTP client, because this supports async much more naturally, and try to replace those legacy types with newer async enabled types step by step. That's a big task for a brownfield project. So step by step.
My question is about this task.whenall that you showed in your slide. If I understood correctly, it is always a string type later, because
no, not necessarily.
How would you make it if there are two?
So the question is when use quickly to find it. So the task.whenall, if it is always string. No, it depends on the types you put in. So you can put in any type. You can put in as a task. So you can put in task or a task of t. What you can do is use it with value tasks, because those combinators, you can then value task, you only can wait once, so you can do that with value tasks. But with tasks, you can put in any, and this returns then one operation that you can await. It doesn't need to be the generic type. Okay, you can put in just tasks. They may be of different types, of different generic types. Because they derive of t, and then once this whenall is completed, all the results are available. So you can access .result of the task without blocking, because the task has completed. So all these individual tasks have completed because the task.whenall operation is done.
So basically, but in case of HTTP clients, you will always have a string in array, right? So
Alfred, can you repeat that?
For HTTP clients in array, you will always expect a string there. So I was thinking that.
So for HTTP clients, if it's always
Like
expecting a string, if I use read a string, so it can also be the stream version of it. But if you use the string part, then
About that
ValueTask, can you clarify when to use the ValueTask and more probably when not to use them?
Excellent question. When to use the ValueTask and when not to use it. So there is a lengthy article from Stefan Pölz about it and a interview on .NET on the on.NET show. So I will all those code and the resources to them. I'm still gathering and put them on GitHub. I will post it into the Meetup channel. I will also put those two resources. But to sum it up, per default, use task and task T. Only if your scenario is a very hot code path and you do a lot of allocation, and most of your tasks, you create a lot of tasks. So if you allocate a lot of tasks, but you know that most of those operations are completing synchronously, then definitely do benchmarking, and then this would be for me an indicator to evaluate ValueTask if I would actually get any benefit from that. And if you definitely don't need any advanced scenarios like the combinators, or if you need to await it multiple times or do some caching, because the task you can just put into a dictionary and then the task can serve as a cache, because you can await it multiple times, but you can't do this with a ValueTask. So if you don't need the flexibility of a ValueTask, and it is a very hot code path, and performance analysis shows that you would save a lot of performance and most of your operations are completed synchronously, then consider ValueTask. Okay, thank you very much. So this was awesome. I was a little bit nervous. Thank you. Thank you very much. So if you still have questions, or if you have some feedback for me, so please approach me. Tell me what was good, what was bad, what was ugly, probably depends. Or write me on the Slack channel or via Twitter. I would love to. I am awaiting your feedback. Nah, okay.
Good. Thank you, Stefan.